Okay, so 1-to-1 means no two inputs result in the same output. And the horizontal line test is analogous to the vertical line test, except that we're drawing a horizontal line, and if that horizontal line passes through more than one point, the function is not 1-to-1. And if the function is not 1-to-1, then its inverse is not a function. If it is 1-to-1, then its inverse is a function. Those are the ones that we care about. For example, the parabola is probably the best example here that we have of something that does not pass the horizontal line test. So I draw a horizontal line. We have two places where the horizontal line passes through a point. It would be like having two y coordinates that are the same, corresponding to different x coordinates, right? So what that means is that if you find the inverse of this y equals x squared, this parabola, its inverse will not be a function. Okay, its inverse will not be a function. Equation of this is y equals x squared. What's the process for finding the inverse? Switch x and y. What does the graph of x equal y squared look like? We won't even solve for y, but that's the inverse. It would be plus or minus the square root of x. Okay? But without even solving for y, we don't need to solve for y. You know what x equals y squared looks like? It's the sideways parabola. Okay, let's draw a sideways parabola. Which way does it open? Right or left? Remember? That's right. And would a sideways parabola be a function? No, because it doesn't pass the vertical line test. Okay, does that make sense? So if it's not 1-to-1, its inverse is not a function. And yes, we do care. See, if I hand you a function, it could be a very difficult algebraic process to find its inverse. You haven't seen that really yet, because you've only been handed problems like factoring. You've only been handed things that could be factored. Okay? But in reality, not every polynomial can be factored. It's the same thing with functions. You've only been handed functions for which you could find an inverse that was probably a function. But it would not be hard for me to come up with a function that it would be very difficult to switch x and y and then solve for y. As a matter of fact, it would be impossible. Okay? But there are ways within calculus that we can work around that. As long as we know that it passes the horizontal line test, therefore its inverse is also a function, then we can deal with it on a point-by-point basis. There are theorems that help us to do that without ever being able to find the actual inverse function, which algebraically we may not be able to do. Okay? You can write algorithms that can do things, in terms of writing application software and stuff, where you can deal with this inverse function without ever actually finding what it is, but do it point-wise. So that's where we're headed with the horizontal line test. So, of course, we're going to be studying exponential functions. Exponential functions, can you picture it? Is it going to pass the horizontal line test? Passing means it only goes through one point no matter where you draw it. So exponential, yes. So exponential is 1-to-1, so that means its inverse, which is the logarithmic function, is in fact a function. Okay, which you already know. I know. That's what we're up to. Okay, so graph to determine if the functions are 1-to-1. So do you have your graphing calculators handy? I'd like you to graph each of these. So I'm going to have this row. Hannah's row is graphing number 1. And graph number 1. Shane's row is graphing number 2. Ryan's row of 2 here is graphing number 3. You're graphing the function.
No, I just don't know what question.
You're not graphing any. You can sit and watch. But what you can do is maybe think about the parent graph, and maybe you guys can answer this question without ever even graphing on your graphing calculator. But I'd like those rows to graph it on their graphing calculator. You got it graphed already? So it says graph to determine if the functions are 1-to-1. So who had the x to the 4th over here? It's not 1-to-1. Why not? It looks like a parabola, kind of weird parabola thing. It kind of goes like that. So this is a no, not 1-to-1 because of that. What about this one?
Yes.
It is. What does it look like? Do you think there might be more to the bottom you can see? So that looks like a J. At least the part that you can see here. Should probably. It's cubic, so it probably does turn down if you.
That makes sense. Yeah. We're still trying.
Okay, so is this 1-to-1?
Yes.
Yes. And then what about the line? And this is, I gave it away. This is just a line, right? So this is a yes. So with a graphing calculator at your disposal, you could quickly and easily graph any function and then tell me if it's 1-to-1 or not. Why do we care? If it's 1-to-1, what does that mean about its inverse? Function, yeah. If we could find it. Here's one right here. If I switched, watch this. If I switched x and y, so here it is, y equals x cubed plus x minus 10. Now let's switch the x and y. X equals y cubed plus y minus 10. And if I said, okay, go, solve for y, what would you do? But I wouldn't be able to teach you because I can't solve for y. It's like we have two different variables here. So, in terms of solving for now, there are things that we can do in terms of solving it point-wise. Your calculator, like we've experienced it before, where the calculator can just point by point plot the points. Like, we always have that option. We're going to actually do that next. Go back to caveman graphing here. You always just start plugging in points, right? You kind of get a picture of what it looks like. That can be programmed in. The calculator can do it that way. All right. Inverse functions and relations. Inputs and outputs are switched. You knew that already. So to find the inverse, this is the process. The inputs and outputs are switched. As a matter of fact, if I wanted the inverse of this list of 4 points, I would just switch the x's and y's. That's it. Okay. So if I want the inverse, I just switch the x's and y's. And so that's the process. If you want to find the inverse of a function, you just switch the x and y and solve for y, and you've got it. Geometrically speaking, the graphs of inverses are a reflection over the line y equals x. So if you've correctly found the inverse, you should be able to plot it on your graphing calculator and see that it is a reflection over that 45-degree angled line going through the origin. That's the line y equals x. Okay. All right, so it says use the chart to graph the function. Then switch the inputs and the outputs from the first chart and write them in the second chart. Graph the inverse. Finally, graph y equals x. So go ahead and do that now. Go ahead and graph the points in the first chart, x comma y. Two different colors here. So -2, 4. 0, 0. 1, 1. 2, 4. That is step 1, graphing that first one. Hey, what do we have but a parabola, right? So what I've claimed is that the inverse is just taking and switching the x and the y. So -1, 1 becomes 1, -1. 0, 0 doesn't change at all. 1, 1 doesn't change at all. But I've switched them. And then here it becomes 4, 2 instead of 2, 4. So if I graph that in blue, there's 4, -2. 1, -1, 0, 0, 1, +1, 4, 2, and I get exactly what you had said before. My perfect example of something in red that is a function, but is not 1-to-1, therefore its inverse is not a function. But these are, in fact, inverses of each other. If I draw in the line y equals x, comes right through here. Do you see that if I folded this over that green line, that the blue graph would land or overlay on the red graph? So they are, in fact, inverses of each other. Now, the inverses are not functions. Inverses don't have to be functions of each other. They are functions of each other if the original one is 1 to 1. All right. Any questions so far? This algebraic process you've already done. This is the process I want you to write down. You may already have it memorized. But algebraic method for finding inverse, replace f of x with y if necessary. Sometimes it's already y equals. Or you could probably skip that step if you understand that this f of x or g of x notation is the same as y. It's the dependent variable here. So replace f of x with y if necessary. Switch x and y, right? This is what you've told. Switch x and y, and then solve for y. So that is the process. And you have a couple options for, so on numbers 5, 6, and 7, it says find the inverse. And then it asks, is the inverse a function? Well, we could tell if the inverse is going to be a function by looking at the original graph, seeing if it's 1 to 1, or looking at the new graph and seeing if it passes the vertical line test. So either the horizontal line test, which tests for 1 to 1ness on the original, or go through this algebraic process we're describing up here and then use the vertical line test to see if the inverse is a function. So I think we already know the answer to the first one, number 5. Can you tell me, is the inverse a function? It certainly isn't. Why not? It's a parabola. The parabola is not going to pass the 1 to 1 or horizontal line test yet. But I think you guys already solved this. You already kind of knew what to do. Switch x and y. So here we go. And then when I go to solve for y, I have to subtract the 3 over. And then I get this 2-part equation, y equals plus or minus the square root of x minus 3. And that's actually the top and the bottom half of a sideways parabola. So is the inverse a function? No. The inverse is not a function. All right, I think we can do this with a rational expression here. So remember, this is actually y, so we're going to switch. You know what to do next on this one? Not really. It's proportion. It's hidden, but it's a proportion. If I do this, you see it as a proportion. How do we solve a proportion? Cross multiply. So I got 4x equals 2y minus 7. You think we can get y by itself now? I think we can handle that, right? So add the 7 over. And divide by 2. So 4x plus 7 divided by 2 equals y. And sometimes what we'll do, you may have talked about this last year, is we will, if this is f of x, we'll call this f with a little negative 1 by it. Did you see this notation last year? Okay. So if they give us a specific function like f of x or g of x, we will oftentimes call it f to the negative 1 of x. It means f inverse of x. Okay. So the question is the inverse right here a function? Well, let me ask you this. What's the parent graph that would go with this? What kind of parent graph does that middle one have? It's a line. Do lines pass the horizontal line there? Yes. So will its inverse be a function? Yes. So yes. So we'll use a little bit of theory here in parent graphs. So that's a yes. If you needed to, you could graph it and see that. All right, now we have a rational function. I think I called that one a rational. That's not rational. That's linear. But here's a rational function. So we'd switch the x and y. Uh-oh. Now what? We're going to mess it up a little bit first, huh? When we cross multiply, we're going to get xy minus x equals 2y plus 1. I don't know if you dealt with these last year when you were finding inverses. You do any inverses of rational functions? They require us to cross multiply, and then we have to do some grouping and factoring here. Because remember, we're trying to get y by itself. So you have any ideas on what we could do next here? We need to get y all on the same side. So we can't divide out yet. Yeah. What's that? Nope, because we could, but that's going to muddy the waters. We need to get the y's on the same side. So we're not going to do any dividing yet.
I'll subtract the 1. And then divide what?
We could subtract the 1, but what do we need? So we can subtract the 1 over, but we need to get this over here. Okay. Somehow we need to get the y's all on one side. So we could go like this. Add the x over and subtract the 2y over. So xy minus 2y equals x plus 1. Do you see what I did? I did 2 steps in one. I added the x over here, subtracted the 2y over here. We are going to eventually divide here. So factor out a y. And I'm left with x minus 2. So you may not have had any rational expressions that you did this process with last year. So you're going to have to remember, get the y's all together, then factor out the y, then divide. Divide by each side. And we have a rational function that begets a rational function here for f inverse. Do you picture in your mind what rational functions look like? Parent graph. Couple of branches here, right? Vertical asymptote at x equals 1, maybe a couple branches here, and here, by the way, this is a good review. You see how I got the vertical asymptote at x equals 1? Yeah. What's the horizontal asymptote going to be here?
2.
Yes, 2. So somewhere through up here.
Oh,
what? So we've got a couple branches up there. Is that going to pass the horizontal line test? Yeah, I think so. So that means what about its function? About its inverse?
It's a yes.
It's a yes. It's a function. And you could graph it on your graphing calculator to help decide. The sound up. Looks like we have some cheering coming on here. It says if two relations are inverses of the balloons, that means there's going to be a cheer here. We're going to be excited about a proof we're about to do. Everybody loves proofs. Verify that f and f inverse are inverses. We actually did this on the front side of these notes of 5-1. We did this already, but now we know about f inverse notation. So it says instead of f of x and g of x, I have now f of x and f inverse of x. So if we're going to prove that these are inverses, what am I asking you to do?
You put this inverse into the spot of x and stuff.
Yep. Put the inverse into the spot of x in the other one. So it looks like this. F of f inverse of x. And so it looks like we're going to take this right here and put it in right here. So it's square root of x minus 2 squared plus 2. What are we hoping this will equal? X, okay. So squaring undoes the square root, so I have x minus 2 plus 2, which equals x. I don't get to cheer yet, because we also have to show f inverse of f of x also equals x. So that's going the other direction. So that means taking square root of, and then we plug in x squared plus 2 minus 2, and show that that equals x as well. So we got square root of x squared plus 2 minus 2 is x squared. This is interesting. This brings up an interesting concept here. We really should talk about the domain of x. Because we're just going to take the positive square root of this, which is x. And then we're going to say, therefore, with our 3 dots, since f of f inverse of x equals f inverse of f of x, which equals x, blah, blah, blah. So, therefore, since f of f inverse equals f inverse of f, and they all equal x, the functions are inverses. Now, I need to talk about this for a minute. I should have not quite given you the whole story here. This should say something about the domain of x in this. Here's the thing. Take your graphing calculator. I'd like you to graph square root of x squared. Tell me which parent graph it looks like. Graph this right here. Square root of x squared on your graphing calculator. Square root of x squared. Yes, it's actually the absolute value of x. Oh. Yeah, that's right. That's one, you're right. So, guys, what's the solution to square root of x squared then, actually?
The absolute value.
Yes, it is absolute value of x. You show that. Yeah, you do now. So, the calculator's not lying. We can cheer here now. Forgot to cheer. Okay. Hooray, the function's there. We proved it. So, but there really should be a, we're just asking for the square root of x squared, just the positive version of it, just the right-hand side of it. Okay, but square root of x squared is actually absolute value of x, because could x have been negative here?
Yeah.
It could be, and then you'd square it, it'd be positive, and you could take the square root of a positive number, so it could be positive or negative. So the calculator's not lying to you. Okay, but there it is. We should have some kind of domain restrictions on that. Let's go through 9 together. This one's always fun. And then we'll just repeat this statement again. But we'll finish this up with 9. The algebra involved in number 9 always, it's a little confusing. So we have f of f inverse of x. And what makes this difficult is that we're going to put a fraction into a fraction. Loads of fun. So we have 3, and then in place of x, I'm going to put negative 2x over x minus 3. And then on the bottom, I have x plus 2.
Do you only sub in x for part of it?
I missed the other one. Nope. Needs to go on the bottom too. So let's fix that. No, you're exactly right. So this is negative 2x over x minus 3. It gets even better if you do it correctly. So everywhere you see an x, you've got to replace it with negative 2x over x minus 3. So that is what we call a complex fraction. It's got fractions inside of fractions. Now what? No, cry. No, don't cry. Water. Okay, so here we go. Right here, this is going to become negative 6x over x minus 3. Here's the goal, guys. We want to get a single fraction on the top and a single fraction on the bottom, and then we're going to flip and multiply, and things will cancel out. Okay. So what do I need to do with this guy to get a single fraction on the bottom? Common denominator, right? That's the one. So, here we go. We have negative 2x plus, distribute the 2x minus 6 all over x minus 3. It looks ridiculous, but we do. That deserves a hooray, huh? Switchy, yes. So we have negative 6x over x minus 3 times, here's the switchy part. The x minus 3 comes up to the top. And what do I actually have on the bottom here?
Just negative 6.
Just negative 6. negative 2x and positive 2x cancel out. So the x minus 3's cancel out. The negative 6's cancel out. I should have waited maybe. Now we can do the array, but you already saw it. We had to do the array because yes, I already saw what was happening. But that's only one direction. Yay! Ooh. We got to go the other. So hooray for that one. We get to do the same thing again. Hooray! And let me leave that up there for a moment so you can finish copying it. Then maybe right next to it, let's go the other direction. I'll let you go ahead and get started on it if you're ready. We still need this part here. I don't have room to do it next to it, so I'm going to do it underneath. I'll have this. Okay, extend down here. So I'm going to go the other direction. So it's f inverse of f of x. F inverse of f of x. So I'm going to put negative 2 times x over x plus 2 and x over x plus 2. So now I'm doing f inverse of f of x. So kind of similar process, negative 6x over x plus 2. Here I'm going to multiply by x plus 2 over x plus 2. The common denominator of x plus 2 on the bottom here. On the top I have 3x minus 3x minus 6. Very similar process. So negative 6x over x plus 2 times x plus 2 over negative 6. Yeah. If you've done it, Craig, it's kind of like using those difference quotients. We know that the h should cancel out if, in fact, I give you a function that has a derivative. So if, in fact, I'm giving you a function that has an inverse, if they are actually inverses of each other, which I'm telling you that, yeah, then this will happen. Yeah. So then you make your statement, therefore they are inverses of each other. All right?